Okay, let's. I want to finish up talking a little bit about electrolysis and some of the implications of what Faraday has discovered. I mean, he came up with this concept of ions, about molecules splitting apart, and each part carrying electric charge, and this is what's going on in electrolysis to generate the electricity. Well, this turns out exactly how a battery works. I mean, Faraday realized that, in the standard case in electrolysis, what you're doing is you're using electricity to drive the chemical reaction. But what is, for instance, water? I mean, you just think about the first electrolysis case that I told you about, water. Well, water molecules don't just spontaneously break apart. You have to, but if you supply electricity, you can get them to break apart. And then that's what drives that electrolysis reaction. Well, what a battery is, it's just like electrolysis, only the chemicals that you've put together spontaneously undergo that process. Okay, you don't need to drive them with an electric current. They actually naturally undergo that process and create the electric current. Okay, so let me just tell you, I'm sure in more detail than I told you before. I might have mentioned roughly, very, very generally how a car battery works when we talked about batteries when we covered Volta, but I know I didn't tell you any of the details. So let me tell you how the battery in your car works. This is actually called a lead storage battery. The reason that car batteries are so heavy is because they've got a bunch of lead in them. One of the in a car battery, you have. I'm not going to try to draw the way the electrodes are actually arranged in the battery, but I'll just draw one cell, and here's my, let me see, let me just draw the electrodes as two flat plates here. And one of these, if you have, one of these plates is lead. Okay, that's, the symbol for that is Pb. And the other plate is lead oxide. And then you put sulfuric acid in solution in between these plates. Okay, so the molecular formula for sulfuric acid is it's 2 hydrogens, a sulfur, and 4 oxygens. Now, each one of these, what's going to, this it turns out, this, as is true with any strong acid, what happens is that the molecule breaks apart very easily. That's what makes, it's one of the things that makes it an acid. And so each molecule of sulfuric acid here, when you put it in solution, will break apart into these 2 hydrogens that each have a positive charge. And then the rest of the molecule which has a double negative charge. Okay, so you haven't created or lost any charge here, right? The two positively charged hydrogens exactly counterbalance the doubly negative charged sulfur oxide ion. Okay, now, what happens at this lead electrode over here is you get the lead reacting with this sulfur oxide ion. And the chemical reaction is lead plus the sulfur oxide with its double negative charge goes to lead sulfur oxide plus 2 negative charges. So this plate becomes a negatively charged, right? This is the negative plate. The chemical reaction that's going on the surface of this plate is going to generate negative electricity. Yes, Troy.
PbSO4 is just the residue that's left on each of the plates.
Exactly. Now you start out, if you start out with a new battery, now you're going to have this negative electrode is just going to start out as lead. As this reaction goes, what's going to happen? It's going to get coated with this lead sulfate. So the lead's going to be turned into lead sulfate. Now at a certain point, when a whole bunch of the lead has turned into lead sulfate, right, your battery is no good anymore, right? And the reaction will stop. That's when your car battery dies. Now it turns out if you force electricity through it in the opposite direction, you can get the reaction to reverse, and that's why you can get the lead sulfate to release that sulfate and turn back into lead, and that's why you can recharge your battery. Yeah, Troy.
Does the 2H plus the PbO2 lead to 2 positive charges?
Wait, which one are you? Oh, are you looking over here now?
Yeah.
Yeah, you're wondering what's going on over here. I was just about to tell you that. Then.
So the battery just keeps going on forever, sort of?
Well, I mean, if you keep recharging it, now there is now at a certain point, you can't even recharge a battery, right? Now what, I'll leave that to Mr. Van Dam to explain. Yes?
How do you recharge it?
Oh, well, I mean, batteries that are rechargeable, the way they recharge them is just forcing electric current to go through the battery backwards. And so and you can get the chemical reaction to reverse. Now, not all batteries are like that. Sometimes there are chemical reactions that give rise to electricity that aren't reversible like that. But rechargeable batteries, that's the characteristic of them, that if you force electricity to go through in the opposite direction that the battery generates it, it actually reverses the chemical reaction.
But the battery can, I guess, go for a long time without being recharged, because
Right.
I've never seen one of my mom's car batteries being recharged.
Oh, yeah, I've had to recharge my car battery a couple of times. It
I think you
What?
have to understand, every time you run your car, it recharges.
Oh, okay.
Every time you
Oh,
turn
right.
on your car, the generator in your car recharges the battery.
Right, right.
And then every time you start it, you take juice out of the battery. Or if you play the radio.
Right. Right, right. So, yeah, the way they design cars now, it's recharged actually while it's run, and you're using that battery only to get the car started or to play the radio when the car's not going, that kind of thing. Yeah.
So the jump cables, they just have to recharge it basically to get the good old juice.
Yeah, but that's to get it. It's gone dead on you, and the jumper cables are just to get the car started, you know. And then once the car is started, if everything's working right, it recharges your battery. Okay, let's look at what's going on the positive electrode here, the lead oxide, and the chemical reaction here is a little more complicated. Okay, let's, you have the lead oxide will combine with 4 of these hydrogens. Okay, let's just start out with 2 of these. Okay. They'll go to 4 hydrogens and 2 of these sulfur oxide ions, right? Okay, now you take this, yeah. Excuse me? No. If you have 2 of these hydrogen sulfur oxide molecules, okay, that's going to be a total of 4 hydrogens, right? But it's only going to be 2 of these guys. I mean, 2 of the sulfur oxides will contain 8 oxygens, if that's what you mean. But it's only 2 of the sulfur oxide molecules. Yeah.
Can you have the H be alone there, or doesn't it have to be H2?
Oh, no, they float around by themselves in solution. It's only when they go into a gas that they hook up. Okay, now, see if you start out with 2 of these, then you can see how both reactions work. One of the sulfur oxides will react on this plate, and the other one will go over here and react on the other plate. Okay, along with the positive hydrogen ions. Right, so you actually have an excess of positive charge here, right? So this is going to go to, again, lead sulfate and plus water plus 2 positive charges. Okay, so you see how these chemical reactions work now. You've always got the same atoms in the same numbers on both sides of the equations. They're just rearranging. And you always have the same amount of electric charge on both sides in the products and the reactants. It's just a rearrangement that's taking place here. You start out with the lead oxide and the positive and negative ions. You end up with lead sulfate plus water plus 2 positive charges. So this is the positive plate. Okay, so you start out with everything electrically neutral, right? The lead oxide, and the acid that you're putting in. But then the acid breaks down into these electrically charged ions, and the chemical reaction that takes place at the plate generates this electricity. So if you have a wire hooked from one of these plates to the other, what's going to happen? You're going to get a current because this plate's getting charged up positive and this plate's getting charged up negative. Yeah, go ahead.
For 2SO negative 4, so it balances out to negative 2.
The
2SO negative.
Yeah, well, each one of these sulfur oxide ions has a double negative charge on it. Okay, so if I have 2 of them, I have a total of 4 negative charges. Now that exactly balances the 4 positive charges, that I have on the hydrogens. Was that your question? Or okay, Troy.
Would the sulfuric acid at all make the lead sulfate corrode the residue? When the residue gets on the plates, would the sulfuric acid at all make it corrode?
Oh, will the sulfuric acid make it corrode? Yeah, there is a. You wouldn't want to have super concentrated sulfuric acid in here because then it's too corrosive on these plates. But like in a car battery, they have it's dilute sulfuric acid, so it's not. It just makes this reaction go. So it is affecting the plates because it's turning them from lead or lead oxide into this lead sulfate. Okay, so you can see how hopefully now you have a little more insight into what exactly it was that Volta discovered in 1800. This is really what's going on in a battery. You've got these atoms and molecules rearranging in these chemical reactions. Breaking apart, first of all, into electrically charged pieces, and then rearranging in ways that leave electric charge on these plates. Now, notice something interesting here. The earlier examples that I gave you when I started out giving you the example, for instance, of hydrochloric acid and a certain amount of hydrogen generating a certain amount of electricity. Okay. Now, notice here that for the amount of lead that reacts, see, every time there's a lead molecule, a lead atom here that reacts, you're getting 2 electric charges, not just 1, for every lead atom. Okay, now, so that's different than hydrogen, where you were just getting 1 charge per atom. And that's what Faraday found. He found that if if you took 1 mole of a substance, reacted in electrolysis, in a battery or in an electrolysis reaction, that it would either generate the exact same amount of electricity that you get from 1 mole of hydrogen, or it would generate exactly twice that amount of electricity. Or there's even some cases, for instance aluminum, where it generates exactly 3 times that amount of electricity. Now what would that tell you? And it's not 1.5 times the electricity, or 1.47. It's either the same amount of electricity you get from a mole of hydrogen, or exactly twice that amount, or maybe 3 times that amount. Daniel?
Once again, it's whole numbers, so it's proof atoms, not even kind of, it's proof atoms.
Yeah, it's whole numbers, but this time it's referring to the amount of electric charge.
So
Right?
each negative charge is proportional to each atom.
Yeah, somehow when you break these molecules apart into ions, what this indicates is if you break these molecules apart into ions, you get either the ions are charged, the same as the hydrogen atom gets charged, or exactly twice that amount, or exactly 3 times that amount. In other words, electricity seems to come in discrete units. Okay, 1 charge, 2 charge, 3 charges, not just any old amount. And this is the first. I don't know how many of you have actually heard the word electron. Okay, well, you've all heard it. This was the very first evidence of what physicists would later discover and identify as the electron. These atoms are not indivisible particles. They have some internal structure, and that internal structure has these charged particles that physicists would later call electrons. And I'm going to give you more evidence for this as we go. But this was the first evidence that, maybe atoms have these electric charges in them, and they can either gain or lose, one charged particle, or 2 charged particles, or 3 charged particles, but they can't. That's why they become charged in these discrete units rather than just continuously charged by any old amount. So this is already evidence pointing physicists in the direction of that there's some sort of atomic structure that is electrically charged. Okay, now let's see, maybe well, let's just take this opportunity. I've given you enough evidence for atoms now. I think that it would be useful to do a little summary of what we've got so far. And you tell me whether you're convinced. Okay, so okay, what's the first big ticket item here? The first really important law that, Evan?
The law of definite proportions.
definite proportions. Yeah, I would. I think. Let me say multiple proportions, because I think that is more direct evidence for atoms, and it subsumes definite proportions. I would say first, Dalton's law of multiple proportions. And remember, just to remind you exactly what that was, anytime you have, I mean, this is you can think of it as the laughing gas law, if that helps. I mean, anytime you have two elements that combine in various ways to produce different chemical compounds, the weights of the weights of one chemical will vary in integer multiples. So it's a consequence. I mean, if you think in terms of atoms, you realize immediately this is the way it has to be, because there can be one oxygen atom, say, in the compound, or 2 or 3, but there can't be, 2.23. So that means the law of multiple proportions has to be true if you believe in atoms. But it's strong evidence for atoms that you have these simple integer ratios of weights. Okay. Next. The next big law that Evan again.
The law of combining volume.
Yeah, that's a good one. Now this one just applies to gases, and it doesn't deal with weights, it deals with volumes. But again, the same thing is discovered, that when gases combine, they combine in integer ratios of volumes. I mean, if you have 2 liters of hydrogen combining it with exactly 1 liter of oxygen to get 2 liters of steam. So it's you have these nice round whole numbers, and that's just a consequence of the atoms combining in these simple integers. As long as you accept Avogadro's law, right? Which says, Nick.
Gases with the same volume have the same number of molecules.
Yeah, exactly. Because there's, what people didn't really expect, the reason this law was surprising was, even if you believe in atoms, it's not obvious that the same volumes will contain the same number of molecules. But if that's true, and then this law of combining volumes has to be true. So again, a law that can be explained by the atomic theory. Next. Daniel.
Allotropes and isomers.
Yeah. Let me see, let's just say existence of allotropes and isomers.
So this is just the order they'd go in.
Yeah, these are I'm just reviewing the major pieces of evidence. Actually, I might as well put years on these things. I think Dalton actually made this discovery in 1803. The law of combining volumes, I believe, was 1808. Isomers was, let me see, by 1827, it was clear that there were isomers. Actually, 1814, Humphrey Davy did his work on diamond. which is an allotrope. What else have we got so far? Troy.
There's the electrolysis, but there's probably stuff before that too.
Yeah, let me see. I covered one other major thing before that.
No.
No. Well, Avogadro I'm covering in connection with combining volumes.
Oh, okay.
Moles and specific heat.
Yeah, the specific heats. I just ripped this thing apart. Wow. Don't know my own strength.
I know that happens a lot.
Okay. Yeah. So let's say Dulong Petit law of molar heat capacities. And that was in 1819. Okay, and remember, I mean, the major point here is just that if you take samples of any element that have the same number of atoms, they'll have the same heat capacity. In other words, if you put the same amount of heat into them, the temperature will rise by the same amount. Okay. And then finally, there's this the electrolysis. So Faraday's law of electrolysis, which again only makes sense when you think in terms of atoms. And as soon as you think in terms of atoms, what Faraday's law tells you is that there's this constant relationship between the number of atoms reacting and the amount of electricity that you get out. And let me see. I told you a year on this one. Nobody, don't say 17. 1832.
Oh, who got it? You guessed.
Now notice, I mean, all of these major discoveries are taking place within a span of 30 years at the beginning of the 19th century. So at the turn of the century in 1800, there's virtually no evidence for atoms. 30 years later, they've already got a pretty solid case going, right? Now you could argue that someone might argue that this is enough. I mean, would you consider the atomic theory of matter proven at this point? Yeah.
You still can't see it.
Well, you still can't see it. I think you can prove them without seeing them. There's think of it this way. You can't really see the gravitational force of the sun on the Earth, right? There's a lot of things you can't see. But Newton proved that one, right? So, no, as long as, the seeing is very important in science. But, all of these laws have to be based on observational evidence, what you can see. But you start with what you can see, and then you do a lot of reasoning, a lot of experiments, a lot of identification of causes, and then reasoning from that reasoning and so on, and you get these very broad laws that you can't see but are nevertheless true. And I think that the weakness in the evidence at this point is, it's not that you can't see atoms, it's that all of this evidence almost all of it, is coming from chemistry. Now, the atomic theory of matter is a very fundamental premise of science, right? We're talking about a fundamental truth about the nature of matter. And yet, physicists haven't been able to, I mean, not much evidence is coming from physics, right? It's all the chemists that are doing all the work.
Isn't Faraday a physicist?
Well, he's a physicist and a chemist. I mean, this law of electrolysis you can think of as involving some physics, obviously. But he's still basically working with chemical reactions here. The only one of these that is physics, that I would classify as physics, is the law of heat capacities. Because they're not working with chemical reactions at all. But you'd like to see more evidence coming from physics here for atoms. If atoms are everywhere, you know, it should be, you know, they shouldn't be just in chemist laboratories. The physicists should be able to find them. And that is going to happen. And it's going to, the way it's going to happen, well, this gives you a hint. The first evidence that did come from physics for atoms came from the study of heat. And that's going to continue. That it's physicists looking into the phenomenon of heat in more detail and starting to think in terms of atoms because of what they're seeing the chemists do. That is what is going to furnish really key pieces of evidence for the atomic theory that come from physics. And that's what I want to do next. Okay, now, let's think about what I've already told you about heat in this class. I think I've mentioned a couple of experiments a long time ago that are important to set the context here. In the 18th century, there were two competing views of what heat might be. One is that, I mean, same thing they thought about electricity, right? That it is a fluid, right? 18th century is famous for its fluids. They thought electricity was a fluid, magnetism was a fluid, heat was a fluid. The competing theory of heat was, does anybody remember? People that denied that it was a fluid, which included Newton, for example. Newton had an idea of what heat was, and it wasn't a fluid. Does anybody?
Electricity or?
No? Daniel. Energy of what? Energy is a concept of action, of motion, right? Nick? Oh, a wave. No, nobody had a wave theory of heat. They just lacked imagination, I guess. But if you come up with one, I'd be interested in it. Newton had the idea, and a lot of other people at the time believed him, that matter was made of atoms, basically. And what heat was, when you heated something up, what you were doing was giving more energy of motion to those atoms. When you were setting them, they were shaking around more, you know, moving around faster. That's what heat was. So, I mean, that's a very different theory than, you know, the fluid theory. It's not a substance at all, heat is. Heat is just this internal chaotic motion of the atoms. Nick? Oh, well, on this view, when you touch a hot object, what's happening? Well, those atoms in the hot object are moving around really fast. Okay, when you touch them, they bang into the atoms in your skin, and they set them moving really fast. Right, right. And it's banging into you with more energy, and you're absorbing some of that energy, and that's what's making you hot. Okay, that's the idea. So I guess that's it for now, and I'll continue that story next week. Not worked out, but he believed in atoms. I mean, he didn't write about it because he realized it was just speculation. But